Section 2.3, Polynomial Functions and their Graphs. So our objectives for this function, for this section, is to identify polynomial functions, find out what a polynomial function is. We're going to recognize characteristics of graphs of polynomial functions, determine end behavior, what's happening at the two ends of the graph. We're going to use factoring to find the zeros of a polynomial function, identify zeros in something called their multiplicities, use something called the intermediate value theorem. We're going to understand the relationship between degrees and turning points, and then we're going to use all of this information to graph any sort of polynomial function effectively. Okay, so first, the definition of polynomial function. So let n be a non-negative integer, and let a sub n minus 1, all the way down, right? We're subtracting subscripts, so all the way down to a sub 2, a sub 1, a sub 0. Let all of those be real numbers, with a sub n not being equal to 0, right? This first term in the front not being equal to 0. A polynomial function is defined, and it looks intimidating, but it's really not when you look at it. So we start with the function, and we start with this first term right there. So that's a sub n with x to the n power. That is just some sort of coefficient. This is just the biggest exponent. Then x to the n minus 1 power is the second biggest exponent. Our ellipses mean everything in between. And then we go down to x to the second, x to the first, and then of course x to the 0 power because there is no x. Okay, so basically all we're doing is we're putting this in order from biggest exponent to smallest exponent. And these numbers in the front are just coefficients. Okay, so we're not going to write the subscripts. It's just a way to make sure that these two, the right coefficient is going with the right number, right? When you see this with numbers in front, it makes a lot more sense. Okay, but this is a standard form of a polynomial function. This is the equation that we are going to use going forward for any sort of polynomial function. And hopefully you've seen it at least a few times before. Okay, so this is a polynomial function of degree n. The number, a sub n, is the coefficient of the variable to the highest power, which is also called the leading coefficient. The leading coefficient and the constant term in the back are going to be really important in the next section when we start to do polynomial long division and synthetic division. So what is a polynomial function? Okay, well, we have to make sure that all of our coefficients in front here are real numbers, and n, the exponent, is a non-negative integer. So let's go back. So this is a polynomial of degree 5 because that's the biggest exponent. Are all of my coefficients real numbers? Yes. Are all of my exponents non-negative integers? Yes. So this first one is a polynomial function, right? It's a polynomial function of degree 5. When I look at g of x, okay, I can kind of see that it's going to be a polynomial function, but I'm not sure what degree it is until I FOIL these two together and then distribute the 3x to the fourth power, the negative 3x to the fourth power, to the rest of the polynomial. And then I can see that it is a polynomial function of degree 6 because that is the biggest exponent, okay? And all of my coefficients are real numbers. All of my exponents are non-negative integers. So what's not a polynomial function is this capital F of x, okay? And it's not a polynomial function because of this term right there, the square root of x. When I write that in exponential form, that's x to the 1/2 power, and that is not an integer. So I cannot have variables with non-integer exponents. Just like right here, that term makes capital G of x not a polynomial function either, okay? Because we have x to the negative 2 power. That is not non-negative, okay? So all of my exponents must be non-negative integers. All my coefficients must be real numbers. So a constant function, f of x is equal to c, where c of x is equal to 0 is a polynomial function of degree 0, right? So if there is no x in the function, it's still a polynomial of degree 0. This is pretty much the way that we write lines, right? It's a polynomial function of degree 1, mx plus b. Happens to be a slope-intercept form. Quadratics, the standard form of a quadratic, ax squared plus bx plus c, where a is not equal to 0, is a polynomial function of degree 2. Okay, so we've talked about constant functions. We've graphed a lot of lines. We've graphed parabolas in the previous section. In this section, we go bigger, right? I think I missed something. Okay. All right, so when we look at polynomial functions of degree 2 or higher, even degree 2 and even degree 1, we think about lines are going to be not really curves, it's just all continuous. But even parabolas are going to be smooth and continuous. Smooth means the graph contains only rounded curves. Smooth, not smooth. Okay? So sharp corners like that means that we're not going to have a polynomial. Okay? In fact, the only way to make sharp corners is to have two different functions. Okay? So that would be a piecewise function. By continuous, we mean that the graph will have no breaks and continue to be drawn without lifting up your pencil from the rectangular coordinate system. That's continuous. There is no way to make this function without picking up my pencil. And here's a picture. Okay, so these two are polynomial functions, the first two over on the left. They have smooth rounded corners, all the corners are smooth and rounded. These are not polynomial functions because they have a break, it's discontinuous, or they have sharp corners. Okay? So you can tell whether something's a polynomial function either by looking at the equation or looking at the graph. I'm not really going to go over too many multiple choice questions here. I'll save those for when I get back to class. But I decided to keep these in because they're kind of useful. Is this a polynomial function? Well, first of all, it's not written in standard form, so I should rewrite it as f of x is equal to 7x squared plus 4x. And when I look at this, all the coefficients are real numbers. All the exponents are non-negative integers, so the answer here is yes. Is that a polynomial function? Well, that is an exponent of -6 because it's in the denominator, so this is not a polynomial function. This is an exponent of x to the, remember, root in the bottom, exponent in the top, x to the 4/3. That is not an integer. Would be an integer if it was, say, the square root of x to the 4th power, because then it would reduce. This is a polynomial function, okay? Because it's okay to have a fraction as a coefficient. That has nothing to do with the exponent, okay, which is to the 1st power. Okay, all the coefficients have to be is real. 5, 1, and 4/3 are all real. Okay? Good. So, end behavior. The end behavior of a graph of a function to the far left or the far right is called the end behavior. Although the graph of a polynomial function may have intervals where it increases or decreases, the graph eventually will rise or fall without bound as it moves to the far left or the far right. And this is true for any polynomial function, right? As we go further to the right, eventually it might do a couple turns, it might jump up and down in between, but eventually it's going to either go up or down. That's one of the properties of polynomial functions. Also, as we go left, it's also going to go up or down depending on a few things. So, how can you determine whether the graph of a polynomial function goes up or down at each end? So the end behavior of a polynomial function, f of x, right? We have our standard form of a polynomial function that we just talked about. It depends on two things. It depends on the leading coefficient and the exponent right there, okay? So we look leading coefficient, exponent, okay? So when the absolute value of x is large, all the other terms, right, as this number, whatever happens to be, whatever I'm plugging in for x, as this number gets bigger and bigger and bigger and bigger, the rest of this stuff is not going to have nearly as much of a effect on the function graph because that's the biggest power, right? When you raise something to the third power, it does way, way more than raising it to the second and raising it to the first and then adding a number at the end. Okay, so this term is really going to have the biggest effect on the function. In particular, the sign of the leading coefficient, a sub n, and the degree n of the polynomial reveal its n behavior. In terms of n behavior, only the highest degree counts. And this is summarized on the next page by something called the leading coefficient test. What is the leading coefficient test? Well, here we go. As x increases or decreases without bound, the graph of the polynomial function f of x is equal to my polynomial function. Okay, I'm not going to say this every time, right? We're just going to call this our standard polynomial function. Eventually rises or falls. In particular, here's what happens. When n is, we sort of have four things. We look at the exponent and we see whether it's even or odd. Okay, we look at the leading coefficient and see if it's positive or negative, depending on the what the exponent is, even or odd. Now we can tell what's going on. So if the exponent is odd, that means that my function, my graph, is going to go in different directions. If it's positive, the graph falls to the left and rises to the right. Okay? And we can use those symbols right there. You can see that the graph is going down this way, going up this way, and who knows what it's doing in between. It could do a whole bunch of other things, right? We don't really know because we don't have the function. But all we know for sure is that it has an odd degree, positive leading coefficient, falls to the left, rises to the right. Okay? If the leading coefficient is negative, the graph to the left rises to the left and falls to the right. So it sort of does the opposite. Rises left, falls right. When n is even, when the exponent is even, the graph does the same thing on both sides. Okay? Positive, they both sides go up. Negative, they both go down. Okay? So they rise left, rise right, falls left, falls right. Okay? Here is a handy chart to help you remember. Okay? So odd degree polynomial functions have graph with opposite end behavior at each end. Even degree polynomial functions have graph with the same behavior at each end, and the table will help you remember that. So we look odd, even, positive, negative. Odd and positive, down then up. Odd then negative, up then down. Even, up, both down. The way I like to remember this is that I know I got to remember that odd functions are going to go different directions, even functions are going to go the same. And if a is positive, the graph ends positive. If a is negative, the graph ends negative, if it's an odd function. With even, if it's positive, they go up. If it's negative, they go down. So that's sort of the way I try to remember these things. Use whatever technique you kind of like. Now, let's try it. Okay, so let's use the leading coefficient test to determine the end behavior of the graph of x to the third plus 3x squared minus x minus 3. So all I really care about here is that term. Okay, so I look at this and I can see that the leading coefficient is 1 and my exponent is 3. So that's a positive and odd number. So a positive and odd number means that this graph falls to the left, rises to the right. Okay, but I'm not going to write it like that. Okay, we don't use these symbols. Those are not really how we're going to do this. So we can actually write it out. We can say that it falls to the left and rises to the right. That's one way to do it. That way is okay, but of course, there's a better way. Okay? When you're talking about what is happening at the end of a function, okay, that is what is known as the limit. Okay? So let's take this one, falls to the left. And as I move to the left of a function, if you think of a graph, right, as I'm going this way, further and further left, what's happening? Well, x is getting closer and closer as we go this way further and further and further and further to the left. X is getting closer to negative infinity. Okay? As this is happening, as I'm going towards the left, this function is going to fall. Okay? That means the function is going to get closer and closer and closer, is getting approaching negative infinity as well. Right? As I go left, the function is going left. The answer to the function is going left. So I can write this with my limit notation. So I can say that the limit as x approaches negative infinity of this polynomial function is negative infinity. Okay? So let's look at this notation one more time. The limit is asking you what's happening as x is getting closer and closer to this number. Where is the graph going as x is going towards negative infinity? Of some graph, what is it equal to? Well, the graph is getting closer and closer to negative infinity. Sometimes limits are equal to negative infinity or positive infinity. Sometimes limits are equal to a number. And yes, sometimes limits do not exist. Okay. Let's try limit notation for the next one. Rises to the right. So that means I'm going right now on this function, which means the limit as x approaches infinity of my polynomial function is going to be, it's rising as I go right. So that means it's going to be going up, which means it's going to be equal to positive infinity. Okay, so this notation is okay, spelling it out, or limit notation is okay, actually writing the limit. I'm not sure how MathXL asked you to put in the answer. I'm pretty sure it is going to be this right here until a little bit later in the section or in the chapter. Okay, so I'll always try to do a second question to make sure that everybody was following what's going on. So here's our first checkpoint question. So use the leading coefficient test to determine the end behavior of the graph. Well, I look right here. I see that the leading coefficient is positive. I see that the exponent is even, which means that this function rises to the right and rises to the left. Ooh, that's not left. Okay. If I want to use limit notation, I could say that the limit as x approaches negative infinity of my function is going to be infinity, and the limit as x approaches infinity of my function is also going to be infinity. Left, it goes up. Right, it goes up. Okay. Next, same question. Use the leading coefficient test to determine the end behavior of the graph negative 4x to the third power times x minus 1 squared times x plus 5. Well, there's a problem with this, is that this is not in standard form. Okay, so in order to make it into standard form, I have to realize that the degree of this term is a 3. The degree of this term is a 2. The degree of this term is a 1. So when I multiply things together, I'm always going to add exponents. Okay, so when I'm taking the first term here, the first term here, the first term here, and multiplying them all together, I'm going to get x to the 6th power. So somehow that's going to be my first term. And I can see that because it's going to be x to the third times x squared when I FOIL this together times another x when I FOIL those together. There's a 1 there, there's a 1 there, there's a negative 4 there. Eventually, when I'm looking at my first term, my first terms are all going to get multiplied together. So my first term of this polynomial is going to be a negative 4x to the 6th power. Now, I could multiply this whole thing to get the polynomial function, but why would I want to, right? All I need is the first term. That's going to be the first term. And I can figure that out by just multiplying all of those first terms together. This one, and this one. And of course, remembering that this one is squared. Okay? So now that I have the first term of my polynomial function, I know what's going on. It is a negative. The exponent is even. That means this falls to the left and falls to the right. Okay? With limit notation, I can say that the limit as x approaches negative infinity of my function, as I go left, it falls, so that's negative infinity. The limit as x approaches positive infinity of my function is also negative infinity because it falls again as I go right. That's going right, that's going left. Because on the number line, going right is going to be towards positive infinity, going left is going to be towards negative infinity. Checkpoint 2. Focus there, focus there, focus there. So that's 2x to the third times x, which gives me 2x to the 5th power. Even and odd, or sorry, positive and odd means that the function falls to the left and rises to the right. How do I know that? Well, I know that because this leading term is positive and it's odd, so they're going to be different, and I want to end on going up. I want to end positive. Limit notation one more time. So the limit as x approaches negative infinity of the function is going to be negative infinity. The limit as x approaches positive infinity of the function is infinity because it's rising. Okay? Next, let's use our leading coefficient test again to model the ratio of students to computers in the United States public schools X years after 1980. Use end behavior to determine whether this function could be an appropriate model for computers in the classroom well into the 21st century. Explain your answer. Well, let's see what's going on here. We have a negative. We have an odd function. That means that this function would rise to the left and fall to the right. Okay, so I don't know what this function actually looks like, and I don't want to graph it. All I know is that on some sort of graph, it's going to be going down. Something's going to happen in the middle. Oh, whoops. It's going to be going up, right? It's rising to the left. Something's going to happen. And then eventually it's going to go down as I keep going further and further to the right. Is this an appropriate model for computers in the classroom? Well, let's think about this. Over the last 40 years or so, 30 years, if you really think about it, the number of computers in the classroom has not gone down. It's gone up. I mean, look at just our school, right? Every year, another class of freshmen, sorry, seniors, another class of freshmen has gotten a Chromebook. Okay, so the number of computers just in our school has been going up in the last 4 years. Okay, so as a trend, this model is not very good because I think we can all agree that the number of computers in school is only going to increase. All right, so bad model, and we can tell that just by using our end behavior. Okay, only one problem for that. Okay, the graph of f of x is equal to negative x to the fourth power plus 8x to the third plus 4x plus 2 was obtained with a graphing utility, in this case, Desmos. Is this a complete graph that shows the end behavior of the function? Well, it's definitely zoomed in, and I definitely have some stuff going on right in here, but is this the right graph? I look at my leading coefficient, and I see that it's negative, which means it goes down to the left, but it's also even, which means it should go down to the right, which means this is not the right graph, and I should maybe zoom out. And when I do, when I change the Y scale, I can see that eventually at almost 600, this graph shoots back down, and I see that now both sides are going down. These turns are kind of in there, but I can't really see them on the bigger graph. Okay, so the bigger graph does give me a better picture of what's going on, as this graph sort of tells me that there's a little bit of a turn in there, which I would have never seen in the zoomed out version. But this graph is not an accurate picture of the whole graph because of the leading coefficient test. It just tells me that this shouldn't be going up, it should be going down. Let's go down to the next question. Same thing. Look at the leading coefficient, x to the third. This is not a graph of x to the third. In fact, it looks like x squared, looks like a parabola. So what am I going to have to do? I'm going to have to zoom out. No. Okay. Well, I know I got the graph over here somewhere. There it is. Okay. When I zoom out, I can see that now this side goes down, this side goes up. And what I'm looking at with the graph on the left is just that little piece right in there. Okay. So not a very accurate representation of the graph. So if you are using a graphing utility, always double check yourself to make sure that, yeah, my answer makes sense. Here, my answer wouldn't make sense because I have an x to the third power, right? I expect the graph to do other things. Okay? So, next section is called zeros of a polynomial function. If f is a polynomial function, then the values for x, which f of x is equal to 0, are called the zeros of the function. These values of x are also called roots or solutions of the polynomial equation f of x is equal to 0. Okay, so that's just a really like a nuanced definition a little bit. So the values for which f of x is equal to 0 are called the zeros. The answers are called the roots. Means the same thing in essence, right? All we're trying to do is find the places where the graph crosses the x-axis, right? So we are looking for x-intercepts of the graph. So how do we find the zeros? The easiest way is to try to factor it. I see I have 4 terms here. We will see other methods to factor something with 4 terms, but for right now, let's factor with grouping. So when I look right here, I see that it has an x squared in common, which leaves me with an x plus 3. Right here, I can factor out a negative 1, which leaves me with an x plus 3 again, which leaves me with x squared minus 1 times x plus 3. And of course, I could keep factoring this piece because it is a difference of squares. Oh, and of course, I'm going to set these equal to 0 to find the zeros of the polynomial function. Okay, so I can solve both of these terms right now, or I can continue factoring x squared minus 1, which is the difference of squares. X plus 1, x minus 1, x plus 3, set that equal to 0. In order to solve a polynomial function, in order to solve any function, remember we find the zeros by setting each factor equal to 0. So x is equal to negative 1 there, x is equal to 1 there, and x is equal to negative 3 right there. Okay, so that makes my zeros plus or minus 1 and negative 3. And if I were to graph that, I would see those are the places where the graph crosses the x-axis. Same thing, I have a I have a cubic polynomial of 4 terms, okay? So I'm going to factor this with grouping. There's other ways that we will see in the next section, but for now, let's do grouping. So I can factor out an x squared there, leaves me with x plus 2. I can factor out a minus 4 there, leaves me with, guess what, x plus 2. Set this equal to 0 to find the actual zeros of the polynomial function, and we're left with x squared minus 4 and x plus 2. Now, let's pretend for a second that we didn't notice that this was a difference of squares. I could always set this equal to 0 as well, add 4 to both sides. So x squared is equal to 4. Take the square root, and of course, when I take the square root in an equation, it always generates 2 answers. And x is equal to negative 2 over here as well. So in this case, we do have a 0 that repeats, and we'll see what that means in a few minutes. Okay. So with this problem, if I want to factor it, which I can, I should always factor out the negative first, okay? And in fact, my first step should be to set it equal to 0. So I can multiply both sides of this equation by negative 1 and make this much easier to solve. And when I multiply the right side by negative 1, that negative 1 just cancels out, turns into 0. Okay? Now I can factor out an x squared because that's what's common with all 3 of these. So x squared times x squared minus 4x plus 4. Factoring this trinomial, of course, gives me x minus 2 times x minus 2, which is x minus 2 squared. Now that I have this successfully factored, I can solve. So this is my first factor, and I set it equal to 0, which means x is equal to 0. Take the square root of both sides. My second factor is x minus 2, and I set that equal to 0, and I get x is equal to 2. Okay. So this graph is going to at least touch, and we'll talk about this in a second, the x-axis is going to have x-intercepts at both 0 and 2. Our checkpoint question, find all the zeros of x to the 4th minus 4x squared. Again, set it equal to 0. Factor out an x squared and set each piece. Well, let's factor this one more time for fun. X plus 2, x minus 2. And it is always good to factor it as far as you can. And that will give you a good representation of what is happening at the function, especially when we go to graph it. Okay, so now x is equal to 0 there, x is equal to plus or minus 2 for these 2 terms. Okay, can zeros of a polynomial function always be found by using one or more of the factoring techniques? Unfortunately, the answer is no. When we look at these functions in example 6 and in example 5, they were all really nice that, in 5 they factored with grouping, in 6 they factored using quadratic techniques and greatest common factor. Unfortunately, that is not going to be our only method to factor and to find zeros of polynomial functions. They get much more complicated, and we'll look at that in the next 2 sections of this chapter. Okay, so little vocabulary here, something called multiplicities. We can use the results of factoring to express a polynomial as a product of factors. For instance, in example 6, we use factoring to express the function's equations as follows, right? When I'm factoring, I can't just make the negative go away, so we're going to have to leave it out front. So this is the same as this example right here. Okay, so we saw that we took the negative out, and then we could factor out an x squared, and then we have our other factor right there. So this factor, x squared, occurs twice because x times x is equal to x squared. This factor occurs twice because it's x minus 2 times x minus 2. Okay? Notice that each factor occurs twice. In factoring the equation for polynomial function f, if the same factor, x minus r, occurs k times, could be once, could be twice, could be as many times as we need, but not k minus 1, we call r a zero with multiplicity k. Right? Basically, we are saying multiplicity means how many times that zero happens. It happens k times, not one more. Okay, not k plus 1. Okay, so for this polynomial function, for this function, we can say that 0 and 2 are both zeros, both with a multiplicity of 2. 0 happens twice, 2 happens twice. Both zeros have a multiplicity of 2. Now, why do we care? Okay, because multiplicities provide us another connection between zeros and graphs. Okay, because this is what we're going towards, right? We factored, we solved polynomials, right, in the start of this to find the zeros. So what we're going to do now is we're going to take those zeros and we're going to give us another way to figure out what's going on the graph, because that's what we're building to here. We're going to graph polynomials. Okay? The multiplicity of a zero tells us whether the graph of a polynomial function touches the x-axis at 0 and turns around, or if the graph crosses the x-axis at the 0. For example, if we looked at the graph of this function, hopefully I included it. Nope, I didn't include it, but that's okay. It looks kind of like it has a 0 and 2. It's going to look something like that. Okay. Trust me on this. Next time I'll have a better picture for you. But if we look at the graph of that function, each 0, 0, and 2 is a 0 with multiplicity of 2. The graph touches the x-axis there, touches the x-axis at 2, and turns around. It doesn't cross. Okay. I also, from before, know that both ends should be going down from the leading coefficient test, which means that the graph falls to the left, falls to the right. Okay. So based on what I know so far, I now have another way to look at these graphs by finding what's happening at the zeros, whether it's touching the x-axis and turning around or crossing through. So if it's an even multiplicity, the graph touches but does not cross the x-axis at the zeros. If it's an odd multiplicity, the graph crosses through. Okay, so that's what this one right here says. If r is a 0 of even multiplicity, the graph touches the x-axis and turns around at r. If r is a 0 of odd multiplicity, then the graph crosses the x-axis at r. And in fact, and regardless of whether the multiplicity of a 0 is even or odd, the graph tends to flatten out near zeros with multiplicity greater than 1. Basically what happens is if you have a 0 that happens twice, at that 0, it's going to look like a parabola. If you have a 0 that happens 3 times, at that 0, it's going to look like a cubic. If you have a 0 that happens once, it's going to go straight through. It's going to look like a line. If it's 4th power, it's going to be flatter. 5th power, even flatter, but looks like a cubic. Okay, so we should kind of know what the basic shapes of x line, x squared parabola, x to the 3rd cubic, x 4th a flatter parabola, x to the 5th a flatter cubic, x to the 6th an even flatter parabola. Okay, so look at those on Desmos. If you're not sure, just plug them in and you can see what those functions kind of look like. Depending on the multiplicity, that is what the graph is going to look like at those particular points. If r is a 0 of even multiplicity, how come the graph of f just doesn't cross the x-axis? because r is a zero of even multiplicity, the sign of f of x does not change from one side of r to the other side of r. This means that the graph must turn around at r. Okay? Think about that for a second. If I have a graph like this, what happens at 0? Well, the graph goes down, it touches 0, and goes back the other way. Because I'm squaring it, right, the sign is not going to change. It's going to be the same sign. However, if it's odd, the sign does change, so it can cross through the x-axis. So let's do this example and find the zeros and their multiplicities. So find the zeros of f of x and give the multiplicity of each zero. State whether the graph crosses the x-axis or touches the x-axis and turns around at each zero. Well, thankfully, this particular function happens to be factored already. So it is nice and easy. Right there. That is not a variable, has nothing to do with any of the zeros. Right there. That's x plus 1. Set that equal to 0, and we have that x is equal to negative 1. That's my first zero. Okay? So what happens at x equals negative 1? We have to decide whether the graph crosses the x-axis or touches the x-axis. And here, it crosses the x-axis. Now at this 0, we have 2x minus 3 squared, which means that x is going to be equal to 3 over 2, which I get by setting that equal to 0. Okay, now it happens twice because it's squared. Okay, which means that the graph touches and turns. Okay, so if I was going to graph this, I would say that the graph goes through negative 1, and at positive 3 over 2, it touches and turns around. I also can notice that that's 2x, that's 4x squared, right? 2x times 2x times another x, that's 4x to the third, times a half, is 2x to the third. So my leading coefficient is 2x to the third, which means this graph falls to the left and rises to the right. So already I have a few building blocks to decide how this graph is going to look. Okay? Not a zero, no variable. X plus 1/2 squared. Please don't get confused with this. Just set it equal to 0. So x is going to be equal to negative 1/2. And that happens twice. So this graph turns at this 0. And x is going to be equal to a positive 5. And because it happens 3 times, it's odd, so it's going to cross. But it doesn't cross in a straight line. It flattens out and goes through kind of like a cubic. Next, we have something called the intermediate value theorem. The intermediate value theorem tells us of the existence of real zeros. The idea behind the theorem is illustrated in figure 2.23, which, look at this, I actually included it. That's good. The figure shows that if a comma f of a lies below the x-axis, this point right here, and b f of b lies above the x-axis, this point right here, the smooth, continuous graph of a polynomial function f must cross the x-axis at some value c between a and b. Let's break this down. If you have a negative output there, a positive output there, this is a polynomial function. If you get a negative output and a positive output, at some point there must be a 0. There must cross. That's all the intermediate values theorem is telling us. Now this is not super useful, okay? Other theorems are a little bit more useful when you come to a graph, but it is important to know what's going on. So let f be a polynomial function with real coefficients. If f of a and f of b have opposite signs, there's at least one value of c between a and b for which f of c is equal to 0. So if f of a and f of b, if you calculate both of those, if they're opposite signs, there's a 0 somewhere in between. So show that the polynomial function, f of x, has a real 0 between 2 and 3. So let's figure out what f of 2 is, and then let's figure out what f of 3 is, and let's compare them. So this becomes 2 to the third power minus 2 times 2 minus 5, which is negative 1. And f of 3 is 3 to the third power minus 2 times 3 minus 5, which is 16. That's negative. That's positive. Somewhere in between somewhere in between 2 and 3, this graph is going to cross the x-axis. So what this tells me now is it gives me a little help when I want to actually graph this, because I don't want to find the 0. I don't want to keep plugging in fractions or decimals to try to figure out what the 0 is. I can maybe find zeros in other ways, which we'll talk about later. But for now, all I know is that this graph will cross the axis somewhere in between 2 and 3, and I should show that on my graph. And if I were to actually calculate it, the 0 is actually 2.09. Okay, so really tough to graph that. Okay, but we know that somewhere in between the graph is going to cross. Let's look at another one. Show that the polynomial function has a real 0 between negative 3 and negative 2. So we're going to find f of negative 3, and then we're going to find f of negative 2, and we're going to compare them. So this turns into 3 times negative 3 to the third power minus 10 times negative 3 plus 9. Okay, so we go 3 to the third power, which is going to be negative 27, times 3 is negative 81, plus 30, plus 9 gives me a negative 42. And then we're going to go 3, negative 2 to the third, minus 10 times negative 2 plus 9. And so we have a negative 24, right? 2 to the third is negative 8 times 3, negative 24, plus 20 plus 9 gives me a positive 5. So somewhere in between these two outputs, there is a 0. So there is a 0 between negative 3 and negative 2. And that is the intermediate value theorem. Next, turning points. So the graph of a polynomial function, f of x, is equal to x to the fifth minus blah, 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 is shown in my figure. The graph has 4 smooth turning points. 1, 2, 3, 4. Places where the graph changes direction. Okay. At each turning point, the graph changes direction from increasing to decreasing, or from decreasing to increasing. The given equation has 5 as its greatest exponent. See that? It's x to the fifth power. Okay. Notice, and therefore is a polynomial function of degree 5. So notice that the graph has 4 turning points. In general, and in bold, must be important, in general, if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. It does not have to have that many. It can only have up to that many. And we can see that by looking at the parent function for x to the third. The parent function for x to the third has no turning points. Okay? Other cubic functions might have 2 turning points, n minus 1, the exponent minus 1. But if I turn 2, 3, if I turn 1, 2, 3 times, that's not a function that's to the third power anymore. Because look, both sides are going down, which means my exponent has to be even. Okay, 3 is not even. Okay? So based on the number of turning points that we see, we can infer what the largest degree the function could be, but it could always be higher, or the smallest degree the function could be. Figure 2.5 illustrates that the y-coordinate, right, the y-coordinate right here, right here, right here, and right here, is either a relative max or relative minimum. Without the aid of a graphing utility or knowledge of calculus, it is difficult to often impossible to locate turning points of polynomial functions with degrees greater than 2. If necessary, test values can be taken between x-intercepts to get a general idea of how the graph rises and how the graph falls. For the purpose of graphing in this section, a general estimate is useful, appropriate, and often necessary. So what does that mean for you? It means that if we have a graph that looks like this, we're not going to go crazy needing to know exactly where these points are, okay? Just what happens at the end, what the intercepts are, and what the general shape of the graph looks like is often good enough, unless we want to get into some calculus. Okay, so that brings us to close to the end, and our general strategy for graphing polynomial functions. So a graphing utility is a valuable complement, right? The Desmos is nice, graphing calculators are nice, but it's not necessary to use this strategy. If you use a graphing utility, some steps listed in the following box will help you select the viewing window that shows you the important parts of the graph. Okay, so this is a 5-part strategy for graphing a polynomial function. Okay, and we should kind of know most of these steps already. Okay, so we have my polynomial function. Okay? There it is. Okay, it could be as long or as big as we want. Step 1, use the leading coefficient test to determine the graph's end behavior. Okay. Step 2, find the x-intercepts by setting the function equal to 0 and solving the resulting polynomial equation. If there is an x-intercept at r as a result of x minus r to the k power in the complete factorization of f, then we look at its multiplicity and decide whether or not the graph touches the x-axis, crosses the x-axis, or if it flattens out near the intercept. Okay. We find the y-intercept by computing f of 0. We use symmetry. We determine whether or not the function is even or odd to help us graph other pieces. And then finally, use the fact that the maximum number of turning points of the graph is always n minus 1, where the degree of the polynomial function, where n is the degree of the polynomial function, to check whether it is drawn correctly. Okay, so that's going to be our check. And then, of course, if we need more information, pick more points to graph. So let's graph this one. X to the 4th minus 2x squared plus 1. Step 1, end behavior. End behavior is going to be up and up. So rises to the left and rises to the right. That means over here, I'm just going to give myself a little note, right? It's got to be going up on both sides. Okay? Next, step 2. Step 2 was to find the x-intercepts by setting the function equal to 0 and solving. So I'm going to say x to the 4th minus 2x squared plus 1, set it equal to 0. Well, I kind of notice that this factors like a quadratic because it jumps from x to the 4th to x squared to no x's. So I can factor this like a quadratic, except instead of having an x in the front, I'm going to have x squared. And the factors of 1 that add to negative 2 is x squared minus 1 twice. Well, those continue to factor to x plus 1, x minus 1, x plus 1, x minus 1, x minus 1, okay, which gives me x plus 1 squared times x minus 1 squared, which means that x is going to equal negative 1 and x is going to equal positive 1, both with a multiplicity of 2. Okay, so this is multiplicity 2 and this is multiplicity 2, which means that the graph is going to, at both positive 1 and negative 1, it is going to touch the x-axis and go the other way. Okay, well, let's get some more information. Step 3. Step 3 was to find the y-intercept. Okay, find the y-intercept by computing f of 0. So if I were to plug in f of 0 to this polynomial function, I would get 0 to the 4th power minus 2 times 0 squared plus 1, 0 minus 0. So f of 0 is going to be equal to 1. Let's put that on my graph. Well, now, I kind of have a basic idea about what this graph is going to look like, because I know that the graph has to touch the x-axis. Well, it has to go through this point, not a straight line, right? It's going to be smooth and continuous. And then at these two zeros, the graph, because they have a multiplicity of 2, is going to touch the x-axis and go the other direction. And it's going to end up going up on both sides. So I can kind of guess that it's going to look kind of like that. But that's a little ugly. And I maybe want a little bit more information. So let's use step 4 and plug in f of negative x to determine whether this function is even or odd, which then gives me negative x to the 4th power minus 2 times negative x squared plus 1. That turns positive, that turns positive, so my function is still x to the 4th minus 2x squared plus 1, which means this function is even. Remember, if I plug in negative x and everything goes back to where it started, it's even. If every single term changes signs, it's odd. And the shortcut is to look at all the exponents here and see they're all even, 4, 2, and 0. Which means this graph has y-axis symmetry. Okay? And I know that it's going to turn, step 5, okay, step 5, it's going to turn 3 times at most. And if I look at this, 1, 2, 3. Okay, so I know it's going to turn 3 times. I know it's going to be symmetric. So maybe I want just one more data point to help me. And so let's plug in 2. So let's find f of 2. And that's going to be 2 to the 4th power minus 2 times 2 squared plus 1. Need a little more room here. Okay, so when I calculate this, 2 to the 4th power minus 8 plus 1 gives me 9. Okay, so I know if I plug in 2, I get 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, look how convenient that is. And because this graph has y-axis symmetry, I know that f of negative 2 is also going to be 9. And now I can draw a pretty good approximation of my graph. Good enough. Again, try to be accurate, but we don't have to be super exact. Okay? So the steps again: end behavior. Step 2, find the zeros. Step 3, find the y-intercept. Step 4, determine symmetry. Step 5, use the number of turning points. And our last step is to get any extra points that I might need to develop a very nice looking graph. Let's try that again. So let's use my 5-step strategy to graph x to the 3rd minus 3x squared. Step 1, end behavior. It is positive and odd, which means the graph goes down to the left, up to the right. So it's going to go down on this side, up on this side. Step 2, set it equal to 0. Okay? and solve, find the x-intercepts. So we say x to the third minus 3x squared is equal to 0. Factor out an x squared to give me x minus 3 is equal to 0. So that means x is equal to 0 and x is equal to 3. 0 has a multiplicity of 2. 3 does not. So what happens? That's a 0 of the function. That's a 0 at the function. Somehow this graph is going to touch the x-axis here and go the other way. It is going to go straight through the x-axis there. And I'm going to infer that the graph is kind of going to look something like this because of the end behavior, that it has to go down on this side and up on this side. Okay, but let's get a little more data before we commit to that. 3. Y-intercept. Find f of 0. Well, that's 0 to the third power minus 3 times 0 squared, which is 0. So not only is, and I can kind of see that on the graph, that I really didn't have to do that one, but we can kind of see that 0 not only is in an x-intercept, it's a y-intercept. Okay. 4. Even or odd? Well, unfortunately, when I look at this, I have an even exponent and an odd exponent, so that means it's going to be neither even or odd. So it has no symmetry on the x-axis, it has no symmetry on the y-axis. 5, it's going to turn twice. Okay? So at most, it's going to turn 2 times because it is something to the third power. Okay, so let's get a few more data points to sort of figure out where this function is, what's going to happen to this function at different points. So I could plug in f of -1, get an answer, f of +1, unfortunately f of 2, to get sort of an idea of what this function is going to look like. And I'm going to graph this real quick. X to the third power minus 3x squared. Unfortunately, I'm not graphing it on this particular computer, but when I do it, I get that f of -1 is going to be about -0.5. So it's going to be yeah, f of -1. Oh, sorry. F of -1 is going to be about -4. Oh, it is going to be -4. So we have this point right here. We have f of +1 is going to be -2. So we have this point right here. And that f of 2 is going to be -4, which is going to be right there. Okay? So we have these 3 data points. So that's -4, that's -2, and that's -4 as well. And I could keep getting more and more if I need to, but that's kind of enough data for me already, because I now can see that the graph is going to look something like that. Okay? And that's kind of good enough. Okay? So, next question. Okay? So now, when we look at this question, we see that it is factored for us, which is kind of nice, because now, number 1, my end behavior is going to be -2 times x squared times x. So it's going to be -2x to the third power, which means it's going to go up, then down. Okay, so rises left, falls right. Okay. Number 2, we are going to find the x-intercepts, but it's factored already. So it's -1. Whoops, let's write this nicer. X is going to equal -1 with a multiplicity of 2. Sorry, x is going to equal to +1 with a multiplicity of 2, and x is going to equal to -2. So that means that at +1 right there, the graph is going to touch the x-axis and go the other direction, and at -2 right there, the graph is going to go straight through. Let's find the y-intercept by finding f of 0. Well, if I plug 0, I will get -2 times 0 minus 1 squared times 0 plus 2. When I plug all these in, calculate this, I get -4. And there's my point. Okay, so now we can try to evaluate the function at different points. So I could try maybe f of, well, let's try 2. So f of 2, I expect the function to be going down to the right. If I plug 2 into this function, I get -8. 5, 6, 7, 8. Oh, look at that. It's doing what I expect. Okay, well, let's plug maybe a negative number in. Let's plug in -1. Well, now if I plug in f of -1, I get -8 as well. Okay, so what's happening here? I expect the function to go up. I expect it to go through this point. I expect it to touch the x-axis and change direction at this point. So I can now kind of graph what's going on with this function. Okay? And there is my graph. Okay, not super pretty, but remember the 5 steps. Step 4 was to determine whether it's even or odd. We have x to the first power there, x squared there is neither. Step 5 was to use the fact that this has x to the third power. We should have 2 turning points in this function, which we do. And Math Excel for 2.3 is not going to be due tomorrow. I think I put the due date to, I don't know, check on Math Excel. And that was 2.3 polynomial functions and their graphs.